What they want to say is that a quantum computer achieves a speed up by just trying all of the possible solutions in parallel. Okay, and now I can explain what's the problem with that. Okay, you can't just do, blind pattern recognition. That's not going to work. And it turns out that all of those wise people were wrong. And popularizers, sort of touting how much quantum computing is going to revolutionize AI. I'm here to tell you that that's like at least 90% BS. So, you can think of it as a race, right? The classical simulations are improving, but the, quantum computing experiments have also been improving. They're already better now than they were 4 years ago. Mm-hmm. Capabilities of deep learning systems have just ridiculously outpaced our ability to explain or understand or predict what they're doing. Right. So it's an amazing system. It's the reason why we can all send our credit card number to Amazon without having to agree, without having to meet an Amazon employee in a dark alley at 4 a.m. to agree on the password. Okay.
Scott Aaronson is the chair of the computer science department at UT Austin and the director of its Quantum Information Center. He's the authority in the field of quantum computing, and his blog is read by everyone who is remotely interested in the field. Most importantly, he is a great communicator of complicated concepts, and that's why I invited him to be on the podcast. Dr. Aaronson currently works with OpenAI on the artificial intelligence safety, so not only we discussed quantum computing, its comparison to classical and use cases, but also the role it can play in AI. But before we start, don't forget to subscribe. And now we start. So what's the most common misconception about quantum computing?
The most common misconception is that a quantum computer would basically be magic, right? More specifically, that it's a machine that would solve any problem, almost any problem instantaneously by just trying every possible solution in parallel. Right. This is what just about every popular article wants to say, that sort of each, a conventional computer based on bits, has to try each possible answer one by one. But a quantum computer could just try each one in a different parallel universe, even if there are 2 to the 1,000th power of them, and then somehow just magically find the needle in the haystack. Right. And people like that because it's easy to say, it would clearly be useful if true. Right. But, unfortunately, nature is not that kind to us. Even with a quantum computer, it turns out we still have to think a lot harder than that to figure out how to actually get an advantage over a classical computer. And, depending on how much time we have, I can explain that.
What is quantum computer and how is it different from classical?
Yeah, so a quantum computer is a proposed, new type of computer that would exploit the laws of quantum physics. Okay, and these are not a new discovery, right? We've known the laws of quantum physics for almost a century, since the 1920s. But this is, you could say, maybe the first attempt to exploit the full weirdness of quantum mechanics for technological benefit. We've exploited it in more limited ways, and without quantum mechanics, we couldn't have built transistors or lasers or so many of the other things that we rely on. Okay, but what quantum mechanics has always said, has been famously bizarre, right? It said that to really describe a physical system, like a collection of atoms or photons and electrons, for example, you can't just list where each particle is and how fast and in what direction it's moving, right? You have to give this much more complicated object, which is called a wave function, right? Mm-hmm. And what is a wave function? It's basically assigning a number to every configuration that the particles could possibly be in. These numbers are called amplitudes. And what quantum mechanics says at its core is that a nature, at least behind the scenes, when we're not looking, is keeping track of an amplitude for every possible way that a physical system could be, for every configuration of the particles that you could see when you look at it. Okay, so so what does that mean, right? A conventional computer is built out of bits, right? And a bit, is either a 0 or a 1. Okay, and usually, even if you're not looking at the bit, well, you might not know which one it is, but you know that it's one of the two, right?
Hmm.
A quantum computer is built out of what we call qubits, okay, which is just the quantum mechanical version of the bit. And a qubit is just a bit that has some amplitude to be zero and some other amplitude to be one. It can be in what we call a superposition of the
Hmm.
zero state and the one state. Now, these amplitudes are actually complex numbers, okay, and that's somehow the key, right? Because if you think about it, even in ordinary life, right, if you didn't know which, whether the bit was zero or one, you might well say, well, I think, there's a 30% chance that it's zero and a 70% chance that it's one. Just like, maybe there's a 30% chance of rain tomorrow. Right.
Hmm.
So even in ordinary life, we're used to, you assign a number to every possible way that a system could be, and then you look at the system and you see that it's in one of the configurations, and then you update your knowledge. We simply call that probability, right? Okay, but and so quantum mechanics, you sort of, the first thing it says is that, at its core, the world is probabilistic, right? We cannot predict with certainty what the
Hmm.
particles are going to be doing when we look at them. We can only calculate probabilities. And, Einstein famously didn't like that, said God does not play dice, blah, blah, blah,
Hmm.
but apparently he does, blah, blah, blah. Okay, but if it was just that nature is probabilistic, that would be sort of somehow much less weird than what is actually going on, right? Because in everyday life, you might talk about a 5% chance or a 30% chance of something happening. You would never talk about a negative 30% chance, right? Much less would you talk about an I percent chance, a square root of minus 1% chance. Okay, but in quantum mechanics, these amplitudes have to be complex. And now there were two different rules for how the amplitudes can change. One for when you're interacting with the system, and another for when you're not. Okay, so if I take a qubit that's in a superposition of the 0 and 1 states, and I look at it in a way that sort of asks the qubit whether it's 0 or 1, then it has to make a choice, right? And then we say it randomly collapses to either the 0 state or the 1 state. Right. And one of the most important rules in all of physics, called the Born rule, explains how that happens. It says that the probability that I'll see some outcome is equal to the square of the absolute value of the amplitude. Okay, so basically the amplitudes become probabilities, right? A higher amplitude means I'm more likely to see that outcome. Okay, but there was somehow this additional information in the amplitudes, before I looked, right? They could be positive or negative. They actually had a direction rather than only a magnitude. Okay, and so there's a second rule, physics for what happens to the amplitudes when my system is isolated. Okay, and that rule is called the Schrodinger equation. Okay, are arguably the most important equation in all of physics. Okay, and basically what it says, it's the central equation of quantum mechanics, and it just says that the list of amplitudes, undergoes some sort of linear transformation. Okay, whose details are left to be specified by the rest of physics, right? But it's some linear transformation, and it always has to preserve the property that the probabilities of all the various outcomes should add up to one. Okay, that requirement is called unitarity. So there is some unitary linear transformation that happens to these amplitudes, and that produces sort of all the weirdness of quantum mechanics. The fact that these amplitudes, evolve via their own rules, and they are different from the rules of conventional probability that we are used to. Okay, so the key phenomenon that tells us that we're dealing with quantum mechanics is something called interference. Okay, now what does interference mean? Okay, it means, if I have a certain event that I'm interested in, like let's say a particle lands on a screen at a certain spot. Okay, and I want to know how likely that event is to happen. when I shoot a particle towards that screen a whole bunch of times. So, well, classically, what I would do is I could just list all the possible paths that the particle could take, and each one contributes some probability to the total, and then I add all those probabilities up. Okay, but what quantum mechanics says is that, as intuitive as that sounds, that's wrong. Right? If it's a quantum particle, then I cannot use that procedure. Instead, what I have to say is that every path that the particle could take contributes an amplitude. Okay, and I have to add all the amplitudes up, and only then I can take the squared absolute value of the sum, and then I get the probability. Okay, so what's the difference concretely? Okay, well, what this means is that I could have some event that could happen one way with a positive amplitude and a different way with a negative amplitude, right? Like, for example, if a particle has two different paths to reach the screen, as in the famous double slit experiment, right? And one path contributes positively and the other contributes negatively. Okay, then it can happen that these two contributions will cancel each other out. So the total amplitude is zero, and that means the particle is never seen in that place. Okay, and now the craziest part is if I block off one of those two paths, I'm going to say I close one of the two slits, now I only have a positive contribution or only a negative contribution, which means now the particle can appear in that place. Right. So to say it again, by decreasing the number of paths that the particle can take to get somewhere, I can increase the chance that it gets there. That's the signature of quantum interference. Okay, so now what's a quantum computer? Okay, well, quantum computer is just this is always the problem when I'm sort of explaining this to journalists. They want a one sentence definition. I'm like, I've been doing this for 20 years, explaining this, and I think I've gotten it down to 5 or 10 minutes. But first, I have to tell you what's quantum mechanics, right? There's no shortcut. Okay, so a quantum computer is a computer that would try to exploit this phenomenon of quantum interference to solve certain specific problems much, much faster than we know how to solve them with today's computers. Okay, so as I said, the basic building block of a quantum computer is a qubit, right? A bit that can be in a superposition of 0 and 1. Okay, but now when I have more than one qubit, okay, something really crucial happens. Okay, and this is called the possibility of entangled states, right? Mm-hmm. So if I have a whole bunch of qubits, then in general, and this is not a new rule. This just follows from the rules that I already said, right? But you cannot just describe the state of each qubit separately from the states of all of the other qubits, right? There might be, for example, some amplitude for two qubits to both be in the 0 state, and then an equal amplitude for both qubits to be in the 1 state, okay? And no amplitude for the qubits to be different. Okay, and what that would mean is that these qubits are sort of coupled to each other. If I look at one of them and see that it's 0, then instantly I know that the other one is also 0. And likewise, if I look at one of them and see that it's 1, right? This is, another thing that Einstein famously didn't like. He called it spooky action at a distance, right? Although, crucially, it was realized early on that you cannot actually exploit this effect to send a message faster than the speed of light. Basically because, you can measure one of the qubits, but you don't control what the outcome of that measurement will be, right? So that's entanglement. Okay, and people have known about entanglement, at least since Einstein, Podolsky, and Rosen wrote about it in the 1930s. And, the first really good experiments, demonstrating the reality of entanglement, that there really is spooky action at a distance, contrary to what Einstein believed, those were done in the 1980s. But basically 2 or 3 particles, right? And not more than that, okay? But now what happens if we have, let's say, 1,000 particles, right? Which can all be in a quantum state together. Let's imagine, for simplicity, that each particle encodes just 1 qubit of information. right? And and this could be all sorts of properties. This could be like, is the particle spinning clockwise or counterclockwise when you measure it, along a certain axis? That's a good example of a qubit, right? Or does the particle have its lowest possible energy, or does it have its first excited energy? Okay, that's another good example of a qubit. Okay, so some property of the particle that can be on or off. And now I'm going to imagine that I've got 1,000 particles. And now the rules of quantum mechanics are unequivocal that to describe what is going on, I now need a list of 2 to the 1,000th power amplitudes. Okay, I need one amplitude for every possible configuration of all 1,000 of these particles, right? If the qubits are all zeros, if they're 0 1 0 1 0 1, if they're 999 zeros and then a 1, right? Whatever it is, if they're encoding the digits of pi, right? Whatever it is, it gets an amplitude. Okay, so quantum mechanics has been telling us for a century that nature is somehow under the hood, it is way more enormous than it looks, right? It's just to keep track of the state of 1,000 measly particles. Nature off to the side somewhere has to maintain this scratch paper with 2 to the 1,000 parameters on it, which is way more than the number of atoms in the whole visible universe. Right. And every time something happens to those particles, it has to, erase those 2 to the 1,000 numbers and replace them with new numbers. So, that's a huge amount of work for nature to be going to, and chemists and physicists have been aware of this for a long time. But, they saw it mostly as a practical problem. Right. If you're trying to solve the equations of quantum mechanics to predict what, interesting molecules will do, this is what makes it so difficult, right? That this exponential explosion in the size of the wave function and in the number of amplitudes that you've got to keep track of. Okay, so it was only in the early 1980s that a few physicists, most famously Richard Feynman and David Deutsch, had the idea that basically if nature is giving us this lemon, why don't we make lemonade out of it? Okay, so why don't we try to build a computer that would itself take advantage of this exponentiality of amplitudes to if nature is so hard to simulate with conventional computers, then turning things around, then shouldn't we be able to build a different kind of computer that is more powerful than the kinds that we currently have? And so that's what they called a quantum computer. And of course, they immediately faced the question, well, what would it be good for? Okay.
Yeah.
And at the time, the only answer that they really had to that question was, well, it would be good for simulating quantum mechanics itself. Okay. Now that's kind of the obvious answer, but I have to admit to you that 40 years after they were writing, I think that I personally think that's still the best answer that we have.
Really?
Right?
Wow.
I think that would at least be the economically most important application that we yet know about, is just giving us this general purpose device for figuring out what any given material or collection of molecules will do, right? It's sort of taming the enormity of the wave function. I mean, that could be useful for designing superconductors, right, rather than this sort of hit and miss process, and it's obviously it's been in the news this week with this LK99. But if you wanted a more systematic way to start, evaluate the properties of materials without having to build them, if you wanted to know the rates of chemical reactions that might be important in industry, does this drug bind to this receptor in the right way? Or design photovoltaics, also for basic physics research, like, research into cosmology and high energy physics, which often involves simulating huge wave functions. I think, a quantum computer could be an amazing enabler for all of that. Okay, but that still leaves a question, is a quantum computer good for anything else? For problems that are not themselves about quantum mechanics? And so here we come head on to that central misconception from all the popular articles, right? Where what they want to say is that a quantum computer achieves a speed up by just trying all of the possible solutions in parallel. Okay, and now I can explain what's the problem with that. Okay, the problem is, yes, with a quantum computer, you can create a superposition, an equal superposition over all the possible answers to your computational problem, even if there's, a 2 to the 1,000th power of them, or whatever. The trouble is, for a computer to be useful, at some point you need to look at it. You need to, measure or observe an output, right? And if I just measure an equal superposition, not having done anything else to it, then the rules of quantum mechanics, the Born rule, tells me that all I will see will be a random answer, right? It will collapse to a random answer. Okay. And of course, if I just wanted a random answer, well, I could have just flipped a coin a bunch of times, right? I didn't have to spend however many billions of dollars to build this quantum computer. Okay. So the sole hope of getting a speed advantage from a quantum computer is to exploit the way that these amplitudes, being complex numbers, work differently from the probabilities that we're used to. Okay, so with every algorithm for a quantum computer, the key idea is to sort of choreograph a pattern of interference among the amplitudes. And it should have the property that for each wrong answer, each answer that I don't want to see, some of the contributions to its amplitude are positive and others are negative, let's say, so that on the whole, they cancel each other out, right? Whereas for the right answer, the answer I do want to see, there I want constructive interference. I want, rather than destructive, I want all the amplitudes, all the contributions to its amplitude to be pointing more or less in the same direction, right? Now, and if I can do that, then when I look, I will see the right answer with a high probability, right? Maybe not with certainty, but that's okay. If I can, I always have the option to just run my whole computation again, right? So, if I had a 10% chance of getting the right answer, then great, I'll just run my computation 10 times and I'll probably see it once, right? So the name of the game is to use interference to boost the probability of seeing a right answer, to way beyond what it would have been classically. Now, the tricky part is that I have to do that even though I don't know in advance which answer is the right one. If I knew, what would be the point, right? And I have to do it faster than the fastest classical algorithm could have done the same thing. Because again, if I'm not beating a classical computer, then what's the point? So I'm here to tell you that no matter what you may have read in the popular press, it is only for a few specific problems that we really know how to do this in a way that gets a big advantage over a classical computer.
Okay? This is a bummer.
Yeah, there's a much wider class of problems for which we can get a modest advantage with a quantum computer. Okay, but if you want an exponential speed up, meaning like a classical computer needs 2 to the n steps, and the quantum computer only needs like n squared steps. Let's say where n is the size of the input. Okay, then that's really only for a few special problems that we know how to get that. The most famous example is the problem of factoring huge numbers. Okay, and here we come to maybe the most famous discovery in the history of quantum computing, which was called Shor's algorithm. Okay, so in 1994, this guy named Peter Shor, then at Bell Labs, was later a colleague of mine at MIT. He discovered a fast method for using a quantum computer to find the prime factors of a gigantic composite number, right? Like let's say a product of 2,000 digit prime numbers, right? You can factorize it quickly using his algorithm. Okay, it was exactly, it was not just trying all the possible divisors in superposition. It was something much more clever than that, that actually achieves this effect of choreographing the interference, right, and concentrating the amplitude on information that reveals the factors you want. In order to do this, Shor had to exploit some very, very special properties of the factoring problem, right? That differentiate it from, most of the hard, combinatorial problems and search and optimization problems that we try to solve with computers. Okay, but why does anyone care about factoring? Well, it just so happens by a sort of amazing coincidence of history that the for better or worse the most of the security of the modern internet is based on the belief that the factoring problem is hard, right?
Oh
Or
wow.
that a few very closely related problems in number theory are hard, right? Anytime you visit a website with HTTPS, okay, or you see there used to be a padlock on your web
Hmm.
browser. I think
Yep.
that they've taken that away, but it's a sign that your communications are being secured by what we call a public key cryptographic code. Okay, and these are amazing codes which were discovered in the 1970s, and which have the property that in order to exchange secret messages, you don't need to agree in advance on a secret key, right? You just, one person can announce a public key that everyone else can use to encrypt messages to them, but those messages can only be decrypted by using a secret key, which that person also has. Okay, now you can think of the public key as like the composite number. Okay, the product of the two huge prime numbers, right? And you can think of the secret key, the thing you need to decode the message, as the prime factors of that number, right? So it's an amazing system. It's the reason why we can all send our credit card number to Amazon without having to agree, without having to meet an Amazon employee in a dark alley at 4 a.m. to agree on the password. Okay. But, the entire scheme is broken if anyone discovers a fast way to factor huge numbers. Okay. And what Shor showed almost 30 years ago now is that if you could build a scalable quantum computer, then you would have that fast method. Hey, again, this is not for all problems. It's not even for breaking all cryptographic codes, right? And we do know other public key cryptographic codes that have resisted, breaking by quantum algorithms, and there is now a push to try to migrate the world to those other cryptographic systems. Okay, but that will be a big effort, right? To
Yeah.
upgrade, every web browser, every router, every server. I mean, there are people still using web browsers that were like known to be insecure in the 1990s, right? So it is very specific to to these few special problems, but the special properties that these factoring and related problems have that let Shor find his fast algorithm for them are directly related to the properties that make these problems so useful for cryptography. So that's the double-edged sword.
Interesting. And I saw the pictures of the quantum computers at Google and IBM. They look similar, like chandelier. Big green,
Yeah,
like,
yeah. So
is
some
it
people
real?
say chandelier. Some people say an upside down wedding cake, right?
Yeah,
But
actually,
but
yeah.
what you're actually seeing there is just the refrigerator for the quantum computer,
Oh,
right?
because it's so.
So
Oh, I see.
yes,
Right.
yeah, exactly. But just to step back, just like a classical computer, has a basic logic that Charles Babbage understood part of, and hoped to realize using just mechanical gears, right?
Hmm.
And Alan Turing, understood parts of, and before the transistor, let alone the microchip, had even been invented, right? And then there are many different physical systems that could implement that logic, right? With a quantum computer, it's very much the same, right? There's this abstract logic of qubits, which is sort of, just clearly pointing to, where we want to get to, right? With any physical, realization. And then there are all different ideas for how are you going to realize these qubits, with actual physics. Okay, so the pictures you've seen are from one particular proposal for most likely for how to build quantum computers, which is called superconducting qubits. Okay, and superconducting qubits is where, well, you build a chip. It's about the size of a normal computer chip, but on it has a bunch of coils that can have a current flow through them in different states, which you could label a 0 state or a 1 state, for example. Okay, but then you take that chip and you put it in a dilution refrigerator. That's that upside down wedding cake,
Yeah.
right? And you cool the chip to like 10 millikelvin, let's say, which is like 100th of a degree above absolute zero, right? So you really want a rather cold temperature here. Okay, and then what happens is that these currents can superconduct, right? And superconductivity is an inherently quantum phenomenon. But one of the things that it means is that now the currents can actually last for some appreciable time in a superposition of the 0 state and the 1 state. Okay, but it gets better because we can actually get neighboring qubits to talk to each other, to undergo 2-qubit interactions that will create entangled states of multiple qubits. And if qubit A talks to qubit B and qubit B talks to qubit C and so forth, then eventually I can get an entangled state of all of my qubits, and I can control which state it is. It doesn't last for very long. Okay, in the state-of-the-art systems, maybe you're maintaining your superposition state for something like 40 microseconds. Okay, 40 millionths of a second. Okay, that doesn't sound like a long time, right? But what's important is that I can do operations on the qubits very quickly. It takes only nanoseconds to do a 2-qubit operation, and that means that I can do hundreds or thousands of different operations on the qubits, while they're still maintaining their quantum state, and then I can measure them and I can see the result. Okay, so that was, if you've heard about this quantum supremacy, quote unquote, breakthrough that Google announced 4 years ago, that was using superconducting qubits. This is also an approach being pursued by IBM, by USTC in China, by a startup company called Rigetti. Okay, but this is not the only approach. There is a completely different approach to building a quantum computer that uses what are called trapped ions. Okay, so here you just take atomic nuclei. For some reason, people use ytterbium nuclei for this. Okay, and each nucleus has a spin state. It can be spinning clockwise or counterclockwise, and you can use that as a qubit. And now you have to keep these these nuclei kind of very isolated from everything else in the world, but you also have to manipulate them in a prescribed way, right? This is always the hard part with building a quantum computer. And the way that people do this is that they trap them in magnetic fields. Okay, so they just sort of trap them in a vacuum, and then they use lasers to manipulate them. Okay, and people have had some pretty impressive results with that too, right? With these various proposals, the state of the art right now tends to be that people can do interesting computations with let's say 50 or 60 qubits and maybe a few thousand operations. That's about where we are now. Of course, eventually we would like to build devices with millions of qubits and billions or trillions of operations, just like we do with classical computers. Okay, that's a very, very hard engineering problem for reasons that we can go into. But when I entered this field 20 years ago, right, it was amazing if you could just get 2 qubits to talk to each other. So, there's clearly been a lot of experimental progress in the last 20 or 25 years. Okay, but other proposals use photons as the qubits. That's being pursued by Psi Quantum, a startup in Palo Alto and in China. There's a proposal to create a new state of matter that's never been seen before, called topological matter with non-abelian anyons. Okay, but if you could do this, then this might support extremely robust qubits. And Microsoft has made an enormous investment into that approach, which you could say is speculative even by quantum computing standards. So all of these different approaches and others that I didn't mention are being pursued in parallel, and we don't really know yet, whether any of them is going to succeed.
And those quantum computers already kind of exist, those experimental ones.
Yes.
Do they solve the problems that classical computers cannot solve yet?
That is a contested question. Okay. So the whole point of these quantum supremacy demonstrations was to try to do that, right? Try to beat classical computing at some task. And it doesn't have to be a useful task, right? Just some benchmark, where, some well-specified problem could be a completely artificial problem, and where a quantum computer will solve it using fewer resources than a classical computer needed. So I was very involved in the design of these experiments, right? I'm not an experimentalist, but around 2010, 2011, my student, Alex Arkhipov, and I had one of the first proposals for how you would achieve, this quantum supremacy with a relatively near-term device. Our proposal used photons, and it was called boson sampling. And, other people had similar ideas around the same time. And then in 2014, Google hired, John Martinez, who was maybe the top superconducting qubits guy in the world. And they said, we basically want to do something like boson sampling, but adapted to our hardware. And so then, we said, we'll accept that challenge. We adapted the theory to the kind of hardware they were building, superconducting qubits. And then they announced the result in 2019. And then since then, other people, USTC in China and Xanadu in Toronto have actually reported quantum supremacy experiments using our original boson sampling proposal. Okay, but with all of these, the dispute is, what exactly, should we think of as the problem that was solved, right? And exactly how hard is it to reproduce the results using a classical computer? Right. And there's a huge amount of back and forth about this. So, infamously, when Google announced its result in 2019, they estimated that it would take 10,000 years to do the same thing with using a classical computer as what they had done with their 53 qubit device. Okay, and then that got repeated all over the press because that sounded like very, very, very impressive, but that didn't last. Okay, like it took only a few weeks for clever, classical computer scientists to say, no, we could do this faster, right? And IBM said, okay, if you use the biggest supercomputer on the planet, which we can't just commandeer at will, it's probably being used for nuclear weapon simulations or something like that. But if we had it, then we could simulate this what's going on in only a few weeks, right? And and they explained how to do that, and and now you could say, well, the quantum computer used about 3 minutes, right? With this proposal with a classical computer, we would need a few weeks, right? But now, with classical computing, one problem is that these simulations are extremely parallelizable. So, you can always reduce the classical time by just throwing more processors at it, right?
Yeah.
And if and we now know that if someone were willing to shell out for, enough processors, which wouldn't even be ungodly many, but just outside the budgets of most research groups, right? Then you could do the same calculation even faster than the quantum computer had done it. right? Okay, but now it turns into a question of, well, what was the metric here anyway? Was it time, or was it ultimately money? Right. Well, money seems a little bit unfair because, with a quantum computer, we have to build the whole thing from scratch, right? And we can't rely on, commodity hardware. Okay, but maybe we could look at energy as the metric, right? How much
Mhm.
electricity is being used? How much CO2 is being generated, right? And by that metric, it looks like the quantum computer is still winning over the best classical algorithms, in the case of the Google experiment, but it's only winning by a couple orders of magnitude, maybe a factor of 100 or something. So I would say that quantum supremacy remains, but it is hanging by a much thinner thread than I would like. And I think that the key now is to do better quantum supremacy experiments that will sort of restore the quantum victory in a more indisputable way, right? I mean, it's, so you can think of it as a race, right? The classical simulations are improving, but the quantum computing experiments have also been improving. They're already better now than they were 4 years ago.
Mhm.
Um, but I would say that a lot of the experimentalists have moved on at this point, right? Like they don't care anymore about this, horse race against
Yeah.
classical, right? Partly because they know that sort of by this route, any victories are just going to be temporary ones. There are reasons for that. Like the way that these experiments work, it takes an exponential amount of time just to verify the outputs using a classical computer, right? Which means that we can't go completely beyond the realm that a classical computer could simulate, because if we did, then we'd be completely beyond the realm where a classical computer could even check the answers, right? And that's why, like, with this
Yeah.
paradigm of experiments, we're always sort of limited to these sort of tenuous advantages. And so the real goal of the experimentalists, I would say, is now, you could say what it was, from near the very beginning of the field, from the mid 1990s, which is to achieve what are called error corrected qubits. So I should explain the fundamental problem here. Qubits, in a sense, are inherently fragile, right? Because I said before that if I have a qubit in a superposition of a 0 state and a 1 state, then and you look at it, then you will collapse it, right, to one or the other. Okay, but crucially, it doesn't have to be a person who's looking or any conscious entity, right? It's any interaction between that qubit and its environment that carries away the information about whether the qubit was 0 or 1 will have the same effect on the qubit as if it was measured. And this is the reason why qubits have to be, so well isolated from their environment, right? You imagine, the environment as constantly trying to measure the qubits and force them back down to being classical, right? And to prevent that from happening, we have to, keep these qubits incredibly well isolated from any, radiation in the room, from the air, from vibrations, from all of this stuff, while still causing them to interact with each other in the way that we want. And this is such a hard problem that there were very good physicists and computer scientists in the 90s who said this is fundamentally impossible. You will never get good enough control over qubits to scale this up. Maybe you'll do little toy demonstrations with 3 or 4 qubits, or maybe even 50, right? But you'll never, get beyond that. And the discovery that changed most people's minds around 1995 or 1996 was called quantum error correction, quantum
Mhm.
fault tolerance. Okay, again, Peter Shor played a central role in that discovery. Okay, also a bunch of other people. And what quantum error correction said was that actually, to build a reliable quantum computer, you don't need perfectly reliable qubits. Okay, you can have, qubits that are, that are interacting with the environment, as long as the interaction is sufficiently small, as long as it's below a certain threshold. Okay, then we can use these very, very clever quantum versions of error correcting codes to get us the rest of the way. to take these qubits that are still noisy and use them to simulate or encode qubits that are less noisy, which in turn could simulate qubits that are less noisy and so on, so that my effective error rate will get pushed all the way down to zero. Okay, so it's kind of like a nuclear chain reaction or something. Okay, it's like if I'm below the critical mass, it's not going to happen. Right, it's like all the things I'm doing to try to correct the errors are just going to be introducing even worse errors than the ones I was trying to correct. Okay, but once I'm below this critical error rate, then I can make my effective error rate lower and lower and lower. So in some sense, the engineering goal of the field for almost 30 years now has been get qubits that are good enough that we can then use error correction to go the rest of the way, and then build as big of a quantum computer as we want. There's been incredible progress. We're not there yet. Okay, but in the latest results from sort of just this year, people can now do 2-qubit interactions with about 99.9% accuracy, right?
Nice.
And when I entered the field, as a student, or around 1999 or 2000, right, 50% accuracy would have been amazing, right?
Wow.
So now it's 99.9%, and in theory there are quantum error correction schemes that should now already work. Unfortunately, they require like an utterly unrealistic number of qubits. Like you might need millions of physical qubits to simulate a single encoded qubit. Okay, but once that 99.9% is improved to 99.99%, so just adding one more nine, then at least on paper, error correction should start to be practical. That's some indication of where we are. Compared to where we were, right? A lot of people complain, well, it's been 40 years, where is my quantum computer? How come I don't have it yet? Okay, so, I think, the most important number to look at is this 2-qubit gate fidelity.
Yeah. You're now in a AI field, right?
Yes.
How can you marry AI and quantum computing if you can?
Yeah, it's a good question. So actually, when I started as a grad student in Berkeley, and this was in 2000, it was not the quantum computing people who recruited me there. It was the AI people. So I spent a year as a machine learning person at Berkeley. And I knew that seemed very exciting. Seemed like it might even change the world on a shorter time scale than quantum computing would change the world. But I was dissatisfied that sort of everything in machine learning seemed empirical. Right? You never had a theoretical explanation for why just about anything worked. Right? It was always just a matter of try it and see. Right. And that is, by the way, that is still the case today, right? Maybe even more so than ever before, right? The capabilities of deep learning systems have just ridiculously outpaced our ability to explain or understand or predict what they're doing.
It's like opposite of string theory, I guess, right?
Yeah, that's right. That's right. Or quantum computing, right? With quantum computing, we've had the theory for decades before, the experimental reality has started to catch up to it. Started to catch up with machine learning. We have the artifacts now, and we're missing the theory. Right.
Interesting.
And so I wasn't sure if I could contribute to a field like that, or if I had anything special to contribute to it. And then I thought that this was in 2000. I thought about marrying quantum computing with AI somehow. Okay, but I couldn't really think of anything to do there that was very non-trivial. Like I could define quantum versions of basic concepts in machine learning, but then I couldn't do that much with them that was interesting. Now, the great irony here is that I merely, needed to have waited for like a decade or so, and I would have learned that actually being, unable to say anything interesting would be no bar to, publishing papers that would get huge amounts of attention, right? So around, maybe 15 years ago, this whole area of quantum AI really exploded, right? It exploded in terms of number of publications and conferences, and popularizers, sort of touting how much quantum computing is going to revolutionize AI. I'm here to tell you that that's like at least 90% BS. Okay. It's for the problems in AI tend not to be these very structured problems like factoring numbers, right? That have these very special properties that we know how to exploit using quantum interference. They tend to be much more unstructured problems. Like, I have a giant space of possible actions and I need to search through it and find an optimal one, right? Or I have this giant inscrutable neural network and I need to, adjust the weights to minimize the loss function. Or I'm playing a game of strategy like chess, and I need a move that's sound against all the moves that my opponent could make. For these sorts of problems, our general expectation is that a quantum computer could someday provide a modest advantage. Okay, and this stems from maybe the second most famous quantum algorithm after Shor's algorithm, which is called Grover's algorithm, okay, which was discovered in 1996. So what Grover's algorithm lets you do is take any problem with a giant list of possible solutions. Let's say there are n of them, right? And where, what I know how to do is just check any given solution and see whether it's correct. Right. And so now classically, if I tell you nothing more than that, then you would say, well, then I guess I need about n steps, or, maybe n over 2 on average. Maybe I'll get lucky and I'll find the solution, half or less than half of the way through. Right. But there's really nothing better to do. Now, what Grover's algorithm lets me do is ask about all of the possible answers in superposition. Okay. But then I don't just immediately measure. Because, if I did that, I just see a random answer. Instead, I do something clever to add more and more amplitude onto the answer that is correct. Okay, and the end result is that I get to see the correct answer, whichever it is, with very high probability after about square root of n steps. So let's imagine that n is 2 to the 100 power. Right, which it could easily be much more than that. I'm talking about a space of possible solutions to a problem, right? So then an exponential speed up would be to like reduce 2 to the 100 down to 100 or 1,000, right? A square root speed up takes that 2 to the 100 and it reduces it to 2 to the 50, right? So still an enormous number, but not quite as enormous as before.
Yeah.
Okay.
Yeah.
So for most AI problems, the kind of speed up that we expect is at most a Grover type speed up. At most that square root kind of speed up. And that's a big problem for, practicality, because, to run a quantum computer at all, there is an enormous overhead cost, right? So, in other words, instead of n versus square root of n, we might be talking about n versus square root of n times 1,000,000, right? Just because of all this overhead to do all this error correction, right? And n actually has to be quite large before the square root of n times 1,000,000 becomes less than n. So, before, this Grover advantage becomes worth it. Even in a hypothetical future world where we've built the scalable quantum computers with millions of physical qubits, and we are using them to run Shor's algorithm and to factor huge numbers, even in that world, Grover's algorithm still might not be a win in practice, right? And so then there would still be a question of, are we going to get an advantage for these AI problems? And if so, how? Right. But, in the meantime, the unfortunate thing that's happened is that people learned that they can just write a paper, about, well, you could use a quantum computer for, vehicle scheduling. You could use a quantum computer for finding, communities in social networks, right? And you could have a quantum version of a neural network, and people will get super excited about that. Like outside of of this field, people will, many people will, like in the business world and the investing world,
Yep.
people will not know to ask the one question that is kind of the crucial scientific question of the field, which is, but are you beating a classical computer that way? Is there any hope that you're going to beat a classical computer, right? What is the advantage, over a classical computer? Okay. And, often they don't even have to lie. They don't even have to say anything false. They just have to not address that one crucial question. Okay. So I think that, we are still looking for a killer app for quantum AI, something that would be as transformative for AI as Shor's algorithm would be for cryptography. That there has been some, excellent research trying to figure out what that killer app would be, but I would say that we don't have it yet, and it remains an active area of research.
If you were 18-year-old today, would you choose to study quantum computing or machine learning?
I think it's entirely possible that if I were 18 right now, I would be thinking about, the revolution of generative AI and large language models, right? Just because, this is, it's one of the biggest scientific surprises, of my entire lifetime, right? That these things work, when they are just, scaled up, I've been around in computer science for 25 years, and I heard all of the experts, explaining why, you will need true understanding of semantics and what language means before you could hope to build any AI, right? You can't just do, blind pattern recognition. That's not going to work. And it turns out that all of those wise people were wrong, right? And it does work. Right. And, hardly any of us predicted it. And I think having failed to predict it, the least we can do is to sort of not be in denial about it, to sort of update on its having happened, and that is so, it is, or sort of so impressive. And it says, it has so many implications for the nature of intelligence, for the future of civilization, that maybe I would want to be involved with that. But that still doesn't mean that I was wrong to pick quantum computing 20 something years ago, right? Because you always have to pick the thing where there is low hanging fruit, where there is an opportunity to make a difference, right? And I felt like, the best, place for that, for me in 1999 or 2000 was quantum computing. And I may have been right about that, even in retrospect.
And it leads me to my last question. You wrote the book, Quantum Computers Since Democritus.
Yeah.
How is this book different from Michio Kaku's Supreme?
Oh my God!
Quantum Supremacy.
You would have to ask, like, how are they the same? They're similar in that they're both written in English.
I saw a blog post about it.
They both contain words, right? They both contain the word quantum. I would say that the similarities end at about that point. I am, trying to give you the honest picture. My goal is not to hype the subject and tell you that quantum computers will do everything. It's also not to tell you that quantum computing is impossible, right? Which is, a position that some of my colleagues have. And, and they could be right, but we certainly, I would say that if they're right, that's way more surprising than if the quantum computing proponents are right. Right. At this point, that you can build a quantum computer that works like the theory says is the conservative prediction. Right. It's it just takes seriously, the physics of the 20th century. But then, the question of what can you do with a quantum computer and when does it beat a classical computer? Right. This turns out to be an extremely subtle question. Right. The answer is sort of much more complicated and interesting than I think any science fiction writer would have had the imagination to invent. Okay. And I'm trying to, give people the, intellectual background that they need to appreciate that. Actually, my book, which is from a decade ago, Quantum Computing Since Democritus, it's less about quantum computing itself than it is about all of the intellectual, background to quantum computing, right? Logic and computability and complexity and quantum mechanics and probability, and just, appreciating all of these basic ingredients that come together in quantum computing in this very, very beautiful way. I do also have lecture notes that are, essentially a book, that are free on my homepage, and which are, just sort of an introductory primer for quantum computing itself. Okay, where again, I am trying to, explain about it. Now, as for Michio Kaku's book, well, I've got a review of it that's up on my
Yes.
blog. You can look at that if you'd
Yep.
like to know just some of the, I went through with a red pen, and it's just sort of, full of, I would say not even inconsequential howlers, but just enormously consequential ones, right? And that come from just sort of not having talked to a single expert in the subject, as far as I can say. And I think I should say many journalists and popularizers have done a much better job than that. I mean, that was bad even by the usual standards of quantum computing.
Yeah, I saw that blog post and I like, oh,
Yeah,
wow, that's
yeah. It was. I mean, it was quite shocking, right? That this person, goes on talk shows and podcasts and so forth as a representative of quantum computing, right? Or like as many millions of people's first exposure to it, right? Like not knowing the first thing about the subject.
I remember there was a time when somebody famous, I think maybe at IBM, said that there is probably total addressable markets for personal computers like 6 or something like that.
Yeah.
And they were wrong. Do you think similar might be with quantum computing?
Well, this is the thing, right? There are these famous quotes about classical computers, right? That people love to trot out, like, that there's a world market for maybe 5 of them, and that there's no reason why anyone would need a computer in their home, right? But and like these seem like some of the wrongest technological predictions in history, right? But if you look at what the people were actually thinking who said these things, right, what they were thinking about was what we would now call the cloud. Right? They were thinking, well, why does everyone need, their own computer? You can just have some centralized servers that will do all the computing, and everyone else can tap into that, right? And in fact, we are moving toward that kind of world, right?
Yeah.
So you could say that those people were obtuse, but you could also say that they were just too far ahead of their time. Right.
Interesting. Yeah. Okay.
And with quantum computing, so like with some trepidation, I would repeat that prediction and say, I don't see any reason why anyone needs a quantum computer in their home. Right. But, the reason why not is, well, why not build the dilution refrigerator and all the other special machinery you need and just have that in a lab somewhere and then put it on the internet. Right. Which is exactly what people are doing right now with the small quantum computers that already exist. Just put it on the internet, and then we all already have our classical computers with which we can access it as a cloud resource.
Thank you very much for your time.